Let us start. As a warm up, we have gone through tensor product. Okay. So, this should be the tensor product of E cross E by E cross E. What do we mean? E is a 2-dimensional irreducible representation. I am taking a tensor product of 2-dimensional irreducible representation with basis states I1 and J1, and this second E with basis state I2 and J2. So, the corresponding reducible representation will have a 4-dimensional basis state, and any arbitrary vector V, if I write it as a column as alpha, beta, gamma, delta, it should be understood as alpha times I1 cross I2, beta times I1 cross J2, gamma times, tell me, J1 cross I2, and then delta will be J1 cross J2. Okay. And then we have also understood how to write the projector for any of these irreps. It depends on the characters in the character table for the irrep E. I want to find what happens to an arbitrary vector. If I take the arbitrary vector to be this, sorry, this gamma should be same as this gamma. If I take an arbitrary vector and the projection for the E dimensional irrep is this, if I do this on this, I end up getting this side, which means I have two independent bases. Okay. If alpha and delta are equal and opposite, beta and gamma are 0, then I will get this basis state. If beta and gamma are non-zero, but alpha equal to delta, then you will get this basis state. So, there are two linearly independent basis states, which is what you should get for a projector of a E dimensional irreducible representation, because the rank of this projector has to be 2, there should be 2 independent bases. Is that clear? We did this, I am just repeating it so that you can recall what we did before the last week, what we did, so that we can get going. Okay. And similarly, you can also show that the projection operator corresponding to the irrep A1, if it operates on the same vector V, it will give you a linear combination of this. Projection operator for A2 will give you a different combination which is orthogonal to this, and it is in fact orthogonal to this and this. Okay. So, the A2 is also one dimensional projector, and you end up getting a projection operator. Projection operator gives you this basis state, and what will this basis states called? These will be the basis states which are called binary bases, right. If you are looking at just the basis, primary basis, it will be either I1 J1 or I2 J2 for the E dimensional representation, right. If you want to look at the A1 basis, binary basis, then the binary basis will be I1 I2 plus J1 J2. If you try to put them as position coordinates, and if these two are different vectors, you can call it as R1 dotted with R2. Okay. So, that is like a scalar which is like the unit representation, and if you have A2 projector, then you get a cross product, that is like your RZ component. Is that clear? Okay. So, with this warm up, let us also recall how to, since I have already said this now, you can see that the A1 irrep in the binary basis will be a dot product of two vectors in the xy plane, which is x squared plus y squared if both the vectors are one and the same, and it could also be just z squared, that could also be a binary basis. These are the primary bases z, rz, it can be x and y, it can also be pure rotations, does not distinguish for you whether it is a polar vector or an axial vector. Why? To see whether it is an axial vector, you have to do a inversion or a mirror transformation, which is an improper transformation. If you are not doing that, you will not be able to distinguish it. So, in this case you can say that x and y, if it transforms like a irrep which is 2-dimensional E, Rx, Ry also will transform like a 2-dimensional irrep E. Another way of seeing is that the sigma v character is 0. Okay. So, in some sense that you can have both are equivalent bases here. If you go to binary basis, this we have, I have also tried to ask you some product of, what was the product? Product of A1 times E. If you take a tensor product of A1 times E, then the characters will get multiplied, right. The characters get multiplied, they are all anyway 1, it does not really matter, you get back E, and the basis for A1, primary basis is Z, primary basis for E is xy. So, you can get binary basis as xz comma yz, okay. That is a 2-dimensional basis, but each one is a binary basis. Okay. Why are we doing all these things? That is the next question you can ask. Why are we spending so much time in understanding position space, primary basis, position space, tensor product giving me binary basis, right. So, you can ask, it looks like a routine monotonous thing we are doing, is there some meaning to it? Okay. So, that is what I am trying to stress now, that whatever you attribute to the position space, you can look at physical observables in nature. What are the physical observables? For example, if I take the electric dipole moment, you all know electric dipole moment of two charges, equal and opposite charges separated by a distance r is q times the distance between them, right. So, what is the nature of that electric dipole moment? Is it polar vector or axial vector? If I write electric dipole moment as q times r vector, is it polar or axial? It is polar, right. It is a polar vector. So, this is one nice observable which is which comes into play whenever we put in some interaction, okay, in the energy with this electric dipole moment into picture, you do need them, okay. So, these are observables, and then if I ask this observable belongs to which irrep, suppose I give you a system which has C3V symmetry, okay, system has C3V symmetry, okay, you can straight away say that Pz observable belongs to A1 irrep, okay. Just looking at the z component, any polar vector z component will belong to the A1 irrep, okay. Similarly, Px Py belongs to E irrep, okay. So, every observable which I am going to do, I can start trying to associate whether this observable belongs to a particular irrep given a system with some group symmetry. I am going to confine myself to discrete symmetry. Okay. So, for example, let me just confine to C3V, let me say that the symmetry of the system is C3V, and then observable, one of the observable is your electric dipole moment vector. You can say that these components of the observable, Z component belongs to A1 irrep, Px Py belongs to E irrep. Okay. Similarly, you can also look at magnetic dipole moment. You all know magnetic dipole moment. So, magnetic dipole moment involves a cross product between current density and the position vector. Once it involves cross product, what is it? It is an axial vector. Okay. So, if you write magnetic dipole moment dV, okay, this is going to be an axial vector. So, now tell me where the Z component will belong. A2 irrep, of course Mx My belongs to E irrep. Okay. In fact, C3V does not seem to distinguish the x and y component whether it is polar or axial. Z component it does distinguish. Clear? So, every observable which I am going to write in nature, I can categorize which irreps it belongs to for a given system with the symmetry which I am looking at. If I am looking at a harmonic oscillator symmetry, then I have to look at it as a C2 group symmetry, and then I have to see which one it will belong to and so on. Okay. So, now I am doing a C3V and I am looking at the observables. Okay. Is this clear? So, as of now these all belong to your primary basis. Am I right? I have not really talked about binary basis, it is just primary basis. Whatever happens to the components of your position space vectors will happen for any of these polar vectors, any of the axial components of the vectors in position space, you can again attribute it to the axial components of your other observables like magnetic dipole moment. Okay. So, this is primary basis. So, I am just trying to justify the bottom line, all observables can be associated with irreps. Okay. So, why we did this elaborate exercise is because we want to look at interactions involving operators for these observables, whether it will trigger a particle in the ground state to go to the next higher state, excited state and so on. If you want to understand, you need to associate irreducible representations to the observables. Is that clear? That is the main reason why I have brought in the basis states, not only basis states, binary basis obtained from tensor products. After that you do a projector and get the binary basis. We have done this elaborately, and the reason for it is that it will help us to understand what are the observables associated with binary basis. That is the next question you can ask, right, and that is coming from tensor products. Okay. You can take two vectors, vector 1, okay, with R1, and then you can also take R2, but you can do a tensor product of this. So, this has 3 components, this has 3 components. Essentially I can write as something which is Qij if I take the ith component of this and the jth component of this. Okay. So, this is something which I can do. If I want to make it traceless, I have to subtract something, but let me just write it as up to some tensor. Let me not even call this to be Q, let me call it as a tensor Tij. Is this reducible or irreducible? It is reducible. Whenever I take a tensor product, the corresponding vector space will be 9 dimensional, which I have written like a 3 cross 3, but it is reducible. And then you will have to do the projectors, appropriate projectors. If you do PE, you will get something. If you do PA1, you will get something. If you do projector A2, you will get something, and they will all be binary basis of the irrevs which you have. Is that right? So, you will get those binary bases out of this. So, one of the examples which I have just, I am sure you have all seen quadrupole moment tensor when you did this expansion in electromagnetic theory course, right. Quadrupole moment tensor, xx component if you try to write explicitly, you will get this answer. Yy if you write it explicitly, you get this answer. Zz is this answer. It is traceless, that is what I said. The quadrupole moment tensor is traceless, and you can also show by symmetry that this gives a 3xy, and xz component and yz component are like the xz in position space up to overall factor multiplying it, which depends on the charges and so on. Now look at the basis, binary basis, which we went through. So now if you want to say which component belongs to A1, can somebody help me out? If you look at this, x squared plus y squared, analog of it is qxx plus qyy. Okay. So, this combination will behave like a A1 irrep in a binary basis. Okay. And this binary basis is extracted by taking tensor product of two vectors and then using a projector. Are you all with me? Okay. So, now tell me what will be the E representation? Is that right? Okay. So, that will be the binary basis representation which corresponds to your quadrupole moment tensor components. So, this belongs to irrep E, this belongs to the summation belongs to irrep A1. You can also have separately QZZ. This is a 1D irrep. And what about A2? Someone? Is that right? Is that A2 or no? Should be, no? Yes or no? QXY will belong to your A2 irrep. So, I have given you some kind of a feel for, so you can still go further, you can find the tertiary basis. What does tertiary basis be obtained from? You take binary basis, tensor product it with one more basis, primary basis, and then start doing projectors and start finding the tertiary basis. Okay? Yeah. I didn't. 2z squared, where is it? 2z squared? Which one? QZZ, there will be a z squared minus r squared. Yeah. So, r squared is like a constant, I am taking it as a constant. So, then z squared is the basis. Anything shifted by a constant, I am not worried. Yeah, then you will get back this, no?
But there will be 2z square minus x square minus 3
Okay, so in some sense you can also write a linear combination if it is a one dimensional basis in some sense. That is another way of doing it. Okay. But here you cannot do that here. There are two independent bases. These are two bases, but then you can also play around with two linear combinations of the bases, right? Yeah. Okay. Any other question? Yeah, I am just taking that r squared is a universal constant. Out, if you remove that, then qxx plus qyy will exactly transform like the A1 irrep, and qzz will transform also like an A1 irrep. That is all I am trying to say. Even if you take a linear combination of two A1 divided irrep, it should not really matter. Yeah. Any other question? Is this clear? Is the motivation clear? We had gone through the drill of doing character table, drill of finding y basis states, y binary basis, y tensor product. Now you can associate every observable either to a primary basis or a binary basis and dot dot dot. It can go to tertiary basis. You know, you can start looking at things. Yeah. I thought it is like a cross product like R is Z, so I was thinking that it should be like, we do not have any basis here, right? I have not written, or it is not allowed. Can we check it? If you take xy, maybe it is not right. Yeah, what you are saying is probably not right. So this is a question mark, whether it belongs to A2 or not, or it is something which has no meaning in this particular group. Some other group it might have meaning, but what you are trying to say is that in the character table xy part we never had. Yeah, I need to see why, but I think xy is not allowed, right? If you do the C3 operation on x and y, you will get a linear combination, and xy will not have eigenvalue as 1. So, I think xy is not allowed. I agree with you. So, this one does not have any place to fit in the C3V character table, but this is a way to do it, like you write it out, look at the binary basis table, this table, and see where the observables can fit in, which irrep it can fit in. That is the theme of this showing you. Yes, qxy does not have any place to put in, I agree.